Bom dia a todos. Good morning. Bom, pessoal, bem-vindo ao nosso segundo dia de evento. Hoje teremos a palestra da doutora Nadine, Essayem. A doutora Nadine, eu vou fazer uma introdução rápida sobre a trajetória. A doutora Nadine é graduada em Engenharia Química na Escola Central de Essayem e tem um mestrado em Química Orgânica e Engenharia Química e um doutorado na Universidade de Poitiers. Logo em seguida, em torno do ano de 93, ela foi contratada pelo CNRS, que é similar ao nosso CNPq, como pesquisadora, diretora de pesquisa, no Instituto de Pesquisa Catálise e Meio Ambiente, o IRC, que em francês é Institut de Catalyse sur l'Environnement, e ela trabalha em diversos campos de pesquisa, particularmente em catálise heterogênea, usando sólidos ácidos e básicos ou sólidos bifuncionais, catálise metal-óxido, ou seja, redox ácido. E vem intensificamente desenvolvendo vários catalisadores, desenho de vários catalisadores, e intensificando sua caracterização das suas propriedades ácido-base e suas aplicações, especificamente nos últimos anos, para a valorização da biomassa. Conversão da biomassa em diferentes biocombustíveis e bioprodutos. Podemos citar que ela vem trabalhando no campo da conversão da biomassa, usando os catalisadores ácidos e básicos, na valorização da celulose nativa ou isolada, para açúcares em torno das cadeias C6 e C5, ou suas transformações em compostos furânicos. A professora, a doutora Nadine, né, que na verdade ela é professora, uma pesquisadora, ela tem diversas colaborações, tanto públicas como privadas, e aprovou diversos projetos para financiamento das suas pesquisas, tanto em governo do governo francês, como em parcerias com outros países e outras instituições. Ela tem uma centena de publicações, mais de 100 publicações, pelo fato de ser um instituto de pesquisa que é bastante vinculado ao setor privado, às indústrias. Ela tem muitas patentes também, em torno de 21 patentes, a maioria delas aplicado à valorização da biomassa, já que é um tema bastante recente dentro do campo da catálise heterogênea. Ela já foi convidada para várias conferências, mais de 50 conferências internacionais e nacionais, e ela também faz parte, devido à sua expertise em catálise heterogênea, ela faz parte do board, do corpo avaliador do jornal Applied Catalysis. E também ela organiza diferentes eventos relacionados à catálise. Ela passou muito tempo na frente do Congresso Ácido-Base, Acid-Base Congress, e também ela já organizou um congresso bastante importante, que é o Congresso Internacional de Catálise e Biorefinarias, que ocorreu, inclusive, em Lyon, na França, em 2017. E, finalmente, é importante, principalmente para os estudantes que têm perspectiva de fazer um estudo fora do país, a Nadine ela tem uma relação bastante próxima, uma colaboração bastante próxima com o Brasil, com as universidades brasileiras. Ela já participou e participa de diferentes projetos, como o tradicional entre o Brasil e a França, o CAPS Coffee Club, e também o nosso doutorado de sanduíche, né, que foi o meu caso. Eu passei um ano no laboratório coordenado pela professora Nadine, através do doutorado de sanduíche. Tá bom? Agora eu vou dizer aqui algumas palavrinhas, antes de iniciar, eu vou dizer algumas palavrinhas em inglês para agradecer a nossa convidada, e em seguida ela vai começar a apresentação. E um detalhe, a Nadine, como nosso outro convidado francês, ela não fala português, ela fala apenas inglês. Ela vai tentar falar bem lentamente, né? Caso vocês sintam intimidado durante as perguntas e perguntar em inglês, vocês podem perguntar em português e a gente tenta traduzir, tá bom? Good morning, Nadine, again. Thank you to accept the lecture. It's really a pleasure to us to share this moment with you. I said during your introduction that you have a close collaboration with Brazilian University, and you participate in several projects such as Doutorado de Sanduíche as my case. Now, Nadine, you can share your slides and start the presentation.
Okay. Okay. I think it works. So do you hear me? So,
Yeah, yes, Nadine, it's work.
okay, I start. So thank you, Dr. Thiago Braga, for the kind introduction. So this is my pleasure to present a conference here, and I would like first to acknowledge all the organizers for this opportunity. And I take this opportunity to present a new research topic in my lab. And the title of my conference is Catalytic Hydrothermal Conversion of Glucose Assisted by UV. And I will present the potential of this new process. So, I did this investigations with mainly my colleague Chantal Quillard, who is an expert in photocatalysis, and as presented by Dr. Braga, I am myself an expert of biomass conversions. So thanks to this both expertise, we try to compare first the hydrothermal conversions of glucose to the photocatalysis process, and we try to investigate a new process, a coupled process, that is hydrothermal conversions assisted by UV. So let me present a little bit the area of all this research. Of course, we are trying to find some alternative to the fossil carbon, and it is now an evidence that lignocellulosic biomass can be seen as a renewable carbon source. And to use this renewable carbon source, we need to develop a more sustainable process. And the general objective of this conference is to validate or not the potentials of a new process which appear in the literatures as regard to the conversion of carbohydrate. This is photocatalysis. And we wanted to compare the photocatalysis process to the hydrothermal process. That was the first objective. The second objective was to explore the coupling of hydrothermal and photocatalytic process. So both processes has the common point to use the same solvent, water, which is the greenest solvent as possible, and which is a favorable solvent for sugar and carbohydrates in general. Both processes have drawbacks. For example, heterogeneous catalysis performed in hydrothermal conversions are performed normally at quite high temperatures and high pressures. That means, as a result, in most processes, the selectivity is quite low. But the advantages of this process is that we can use some high concentration of substrates, and we obtain quite high rate of reactions. By comparison, photocatalysis, who use also water as solvents, is usually performed at quite low temperatures, at ambient temperatures. And generally, the main drawbacks of this process is photocatalysis works only with very diluted substrates, and usually the reaction rates are quite slow. But the advantages of photocatalysis as regard to the hydrothermal process, usually the selectivity is higher. A common point between these two processes is the use of titanium dioxides. Indeed, titanium dioxide is a semiconductor, and this is the more efficient photocatalyst. And titanium dioxide can be used also in the hydrothermal process due to its acidic and basic properties. Let's start with a few words about the titanium dioxide. Titanium dioxide exists under different crystallographic structures. The most known and used are anatase and rutile. The phase transition between anatase and rutile occurs at temperature higher than 600 degrees C. Titanium dioxide is known to be a very hydrothermal stable oxide, and titanium dioxide possesses as well acid and basic sides. But we can say that there is no agreement in the literatures about the natures of the acid sites in particular. In most of the publications describe the presence of Lewis acid sites, which are also water tolerant. That means the sites work in water. The presence of Brunstedt acid sites over titanium dioxide, is still under discussions. There is only few articles which report the presence of Brunstedt acid sites. And as regards the basicity of the titanium dioxide, it's the same. Only few articles describe the basicity of titanium dioxides. So let me start now with a few words about the hydrothermal conditions. It is important to recall that working in hot water, there is some difficulties which can be some advantages in some cases. Hot water is in fact a reactive solvent. This is due to the self-protolysis of water. Water is dissociated into protons and hydroxyl anions, and this equilibrium is right shifted with the temperature increase, and we have the highest concentrations of protons close to 200 degrees C. So hot water is a reactive solvent. That means that we have homogeneous active spaces in hot water. And when we want to make reactions using carbohydrate and, for example, glucose as substrate, just putting sugar in water at high temperature, we can obtain already different molecules, but we obtained also a lot of oligomers. And if we want to control the selectivity of these transformations, we need to work with additions of catalyst. A favorite catalyst is a heterogeneous catalyst. In our case, we choose to work with acids or bases. But we have two solutions. We have to decrease the temperatures in order to reduce the activities of these homogeneous spaces in order to control the transformation at the surface of the catalyst, or we have to play with the complementarity of the homogeneous active spaces and the sites which are present on the surface of a solid catalyst. So what is reported in the literatures as regard to the chemical transformation of glucose in hydrothermal conditions in the presence of titanium dioxides? Let me talk about the pioneering work of Watanabe, who reported the production of HMF, hydroxymethylfurfural, using rutile titanium dioxides. Anatase was reported to be inactive. Rutile was active, and that was explained by the author by the presence of as well acid and basic sites at the surface of the rutile titanium dioxide. The basic sites promote the isomerization of glucose into fructose, and the acid sites can promote the dehydration of fructose into HMF. We can mention also the work of ARA, who reported also high yield in HMF, but using a phosphated anatase titanium dioxides. And the activity of this type of catalyst is related to the presence of phosphate on the surface of anatase. We can also mention a work which was performed in methanol as solvent using anatase titanium dioxides, and we obtained methyl levulinate. But they explain this selectivity to the presence of traces of sulfur at the surface of this titanium dioxide. In absence of sulfur, the catalyst was inactive. So now it is important also to recall what is the basic principle of photocatalysis. Photocatalysis consists of the irradiations of a semiconductor, the titanium dioxide particle, with photon. And when the energy of this photon is higher or equal to the band gap of the semiconductors, we have an excitement of the electrons of the valence band to the conduction band. And we have a formation in that case of positive holes and of electrons in the conduction band. And these two species can promote as well oxidation reactions or reductions. So let me now report what is reported in the literature as regard to the catalytic conversion of glucose catalyzed by titanium dioxide. Using a biphasic media, water and acetonitrides, it was reporting that it was possible to produce gluconic acids as well as glucaric acids starting from glucose under air, and in pure water under these conditions, instead of productions of this type of gluconic glucaric acid, we observe the complete mineralizations of this carbonaceous compound into CO2. In neutral atmospheres, it was also reported a quite high yield of shorter sugars, a C5 sugar as arabinose or a C4 sugar as erythrose, starting from the C6 sugar glucose, but using rutile titanium dioxide modified with rhodium, noble metals. Lactate was also obtained by photocatalysis using titanium dioxide, but in the presence of sodium hydroxide. So, and the mechanism which explains the formation of all these intermediates in addition to the final formations of CO2 when the transformation is performed under oxygen or air, is that why? This is in fact a successive step of oxidative decarboxylation. The first step is the oxidation of glucose into gluconic acid, then oxidative decarboxylations into C5 sugars, arabinose, and then it continues in the same way with the formation of the arabinoic acid, then its oxidative decarboxylations to form shorter sugars up to the complete transformation of this intermediate into CO2. Under anaerobic conditions, under argon or nitrogen, we have a mechanism which is described as an alpha scission pathway. We have decarboxylation of the sugar into all the shorter sugars. Glucose is converted into arabinose with the release of formic acid, then the formation of erythrose, etc., etc. But in that case, it is mandatory to work with titanium dioxide modified with noble metals. This is to avoid electron-hole recombinations. So the methodology of our investigations was the following one. Since titanium dioxide exists under different crystallographic structures, we've selected to work with commercial titanium dioxides. We choose a pure anatase, UV100s, a pure rutile, Ru 160s, and a reference titanium dioxide P25. Since we know that there is no agreement in the literatures about the acidity or basicity of the different crystal phase of titanium dioxide, we started our investigations by the characterizations of the superficial properties of the titanium dioxide. We investigate acidity and basicity using infrared spectroscopy or calorimetry in order to investigate the absorption of common molecules. But we investigated also the absorptions of glucose in water because a priori we thought that this is probably an important step and maybe the limiting step. And then we started to investigate the reactivity of these 3 different titanium dioxide. First, we investigate the hydrothermal conversions and the photocatalytic process separately, and after, we investigate the hydrothermal process assisted by UV irradiations as well under air or under neutral atmospheres. We wanted to investigate this new process to try to understand the phenomenon and to try to observe the relation between the structures of the titanium dioxide, its superficial properties, and the reactivity. Okay, let me continue with the characterization of the different titanium dioxides. So we selected one pure anatase, UV100, one pure rutile, and P25, which is a mixture of rutile and anatase phase. The different titanium dioxide present different surface ability. The lowest one is obtained on the reference catalyst, the P25. The pure anatase has a very high surface area, 300 square meters per grain, and the rutile has also quite high surface areas. Here I present the characterizations of the 3 titanium dioxide using pyridine adsorptions investigated by infrared spectroscopy. The spectra were normalized to the same weight of the pellets of each catalyst. we can observe that on the free titanium dioxide, we observe the typical vibrations of a Lewis acid sites, but we can notice the absence of characteristic vibrations of a pyridinium species, which is formed by interaction of pyridine with protons, Brunstedt acid sites. So even in the case of a reference catalyst, the P25s, even if we have a very bad background, we do not have evidence of the presence of Brunstedt acid sites, whatever be the structures, rutile, anatase, or the mixtures of both. Let's continue with the calorimetry of NH4 adsorptions in order to quantify as well the number of acid sites and their strength. On the left, I represent the isotherm of ammonia adsorption of the free titanium dioxide, and we can observe that the pure anatase present the highest amount of acid site, followed by the rutile and the reference P25. On the right, we have the calorimetric curve, which represents the heat of adsorption of ammonia on the solids, which represents the strength of the acid sites as regard to the coverage of the surface with ammonia. We can observe that the pure anatase titanium dioxide presents the highest heat of ammonia adsorptions and has the strongest acidic surface. By contrast, we can observe that the pure rutile has a quite heterogeneous surface without plateau. In the case of the P25, we have a very short plateau, but the heat is quite lower than the one measures on the pure anatase phase. Since the catalyst has different BT surface area, we calculate the acid site density, which is expressed per micromoles of ammonia or micromole of sites per square meters. And we notice that the highest density of acid site is obtained on the P25 with a density close to that of the pure anatase phase, and the rutile has the lowest acid site density. We did the same as regard to the basicity using CO2 as probe molecules adsorptions. The isotherm show also that the pure anatase phase has the highest amount of basic sites, then the rutile, and the lowest amount of basic sites is obtained on the P25. And as regard to the strain, the calorimetric curve show that the pure anatase phase has the highest heat of ammonia adsorption, followed by the rutile, which still has a quite heterogeneous surface as regard to the basicity. And we can also say that the reference catalyst, the P25, has almost no basic sites. And we calculate also the density of basic sites, and the highest density is determined on the pure anatase phase, followed by the rutile, and then the P25. We investigate also the glucose adsorptions on TiO2 in water. And we observe that the P25 presents the highest capacity to adsorb glucose in water, followed by the anatase and the rutile. So this slide summarizes the different characteristics of the titanium dioxides. So as we go to the structures and texture, the P25 has the lowest BT surface area, the pure anatase the highest one, and the acid-base properties was summarized in this table. And we show that the highest Lewis acid site density is determined in the P25, and we can notice that the reference titanium dioxide P25 presents also various capacity to adsorb glucose in water. then pure anatase has an intermediate capacity to absorb water, and she has also an intermediate Lewis acid site density, and then rutile. Then we propose that the absorptions of glucose in water may be correlated with the density of the Lewis acid sites. As regards the balance between acid and basic site on the surface, we can notice that the rutiles presents the most basic surface, then anatase, and the lowest basic titanium dioxide surface is the one of the P25. Now let's shift with the reactivity of these three different structures of titanium dioxide. To perform our investigations, we use, in fact, a batch-type reactor, an autoclave, which is equipped with a window which on the bottom of the autoclave, which allow irradiation with UV. And to conduct in the same reactors as well hydrothermal process, photocatalytic process, or the coupled process, we use exactly the same concentration of glucose, the same concentration of titanium dioxide, and we selected a value which is intermediate because what is usual for hydrothermal process and photocatalysis. We investigate temperature from ambient temperatures to 150, and the pressure can be increased up to 20 bars. So we investigate first pure hydrothermal process, that is, we perform the reactions between 120 and 150 degrees C in absence of irradiations. For the pure photocatalytic process, we perform the reaction at ambient temperature but under UV irradiations. And for the coupled process, that is to say hydrothermal process assisted by photocatalysis, we combine both temperatures between 120 and 150 and UV irradiations. So let me start by the pure photocatalytic transformations performed at low temperatures under air atmosphere. This figure compares the conversion of glucose obtained with the free titanium dioxide, and we observe that the most efficient is the reference P25. And if you remember the characterization I just presented, the order of activity observed in photocatalysis follow quite well the glucose absorption capacity of a different titanium dioxide, and this can be linked to the density of the Lewis acid sites. As regards to the selectivity to the different products we analyze in the liquid media, there is no huge differences between the three different titanium dioxide. We observe the main products we obtain in this curve present the yield of a different product obtained with the reference titanium dioxide with the extent of the reaction with the glucose conversion up to 100%. We observe the main formations of arabinose, erythrose, but also formic acid and gluconic acid, and we can observe the disappearance of all the products when the glucose conversion achieves 100%. And all the product we observe in the media during the course of the reactions is in good agreement with the mechanism reported in the literatures, where we have first the oxidation of glucose in gluconic acid, After an alpha scission to produce arabinose and formic acid, then the formations of erythrose, etc., up to the formations only of CO2 in gas phase. That is why we do not have any products in water at the end of the reactions. Now let me compare the reactivity of the free titanium dioxide in pure hydrothermal conversion. That means at high temperature, 120 degrees C, under air, but in absence of irradiations. In that case, the reference catalyst, the P25, present the lowest activity. The more active catalyst is the rutile phase, and the intermediate one is the anatase, titanium dioxide. After 4 hours, the rutile and the titanium and the anatase present the same conversions. When we look to the carbon balance it is determined by a total organic compound analysis at the end of the reaction. With the P25, the carbon balance is excellent. It's not the case for the two more active catalysts, and this is explained by the mineralizations of part of the substrates. But if we look to the initial rates of glucose conversion, the highest initial rate is obtained with the rutile phase, and the rutile phase is the titanium dioxide, which present the highest balanced basic acid sides balance. And we can deduce from this result that hydrothermal glucose conversion promoted by titanium dioxide is quite sensitive to the basicity of the titanium dioxide used as catalyst. Now let me discuss a little bit about the selectivity of this transformation. First, this figure represents the different products we analyzed using the rutile catalyst. And with the rutile, the titanium dioxide, the main products is fructose. And we know that fructose is a tracer of the basicity of the catalyst, and this is in good agreement with the previous characterizations we have presented before. Using a pure anatase TiO2, the main products are still fructose, but we have also formations of gluconic acid. And in that case, we can conclude that the selectivity is rather tuned by the acid-base balance of the titanium dioxide. We can see that fructose is favored using the most basic rutile titanium dioxide, while gluconic acid is favored using a more balanced surface in terms of acid and basic sides, which is the pure anatase phase. And we can also observe that we obtain a quite high selectivity in gluconic acid, and when we continue the reactions for 1 day, we obtain close to more than 60% yield in gluconic acid, and we can conclude that the pure anatase is a quite efficient novel metal-free catalyst for glucose oxidation in gluconic acids. So, to summarize all the transformations we observe over titanium dioxides, we reported here all the different states which are promoted as well by the basic sites, which are the oxygen atoms of the oxide, or by the Lewis centers bound by the titanium cations. We may have oxidations of glucose into gluconic acid. We observe also the cis cleavage of glucose into erythrose and shorter carboxylic acids. We observe also the isomerization glucose-fructose and the further transformation of glucose in shorter molecules by CC cleavage. We observe also HMF formations, and HMF is promoted by branched acid sites, which are probably due to the presence of course, water self-photolysis, but also the dissociations of some carboxylic acid present in the media. So, to summarize, what we have observed comparing the two independent processes, hydrothermal or photocatalytic process, as regard to the conversion of glucose over titanium dioxide, we can underline that we have, validate the potentials of photocatalysis as regard to the hydrothermal conversions of glucose, since we have observed glucose conversion and reaction rate in, which are quite equivalent. Knowing that photocatalysis is performed at ambient temperatures and hydrothermal conversion at more than 100 degrees C. And we have observed that photocatalytic activity would rather depend on the glucose absorption capacity of titanium dioxide in the water, which can be correlated with the Lewis acid site density. By contrast, for hydrothermal conversion at high temperatures of the titanium dioxide, we have observed that the main driving force for the conversion of glucose is rather the Lewis basicity of the titanium dioxide rather than the Lewis acidity, and that the selectivity serves to tune the selectivity is tuned by the balance between Lewis and Lewis acid and base balance of the titanium dioxide surface. And we have evidence that we can obtain quite high yield of gluconic acid just using titanium dioxide in absence of noble metal and in absence of soluble bases. Now, let me continue with the new process coupling hydrothermal conversions and photocatalysis. For that, in the autoclave, we work at high temperatures and under UV irradiations. On this slide, we can compare the three titanium dioxides in the three different processes. Each figure represents the conversion of glucose with the course of the reactions. The black line represents the conversion of glucose obtained with the coupled process. The blue one, the one observed in pure photocatalysis process performed at low temperatures, and the red one is the conversion of glucose obtained in hydrothermal process. That means at high temperature, but in absence of UV. We notice that whatever the titanium dioxide we use as catalyst, the conversion obtained in the coupled process is always higher, superior than the conversion we obtained in hydrothermal conversions and, of course, in photocatalytic process performed at low temperatures. Only in the case of a reference catalyst, the P25, we observe a synergy between the photocatalysis process and the hydrothermal process, with the conversion quite higher than the one we obtain in hydrothermal process. This cannot be evidenced using the pure anatase of a pure rutile, because these two titanium dioxide has already a high conversion in hydrothermal process. So, under here, let me discuss about the selectivity of the conversion on the UV100 catalyst, which is the pure anatase. This figure represents the evolution of the yield in the different products as regard to the conversions of the glucose. we do not observe new products. We observe the same gluconic acid, arabinose, erythrose, and so on. But we observe also the disappearance of a product with the course of a reaction without no more products at full glucose conversions. And when we look to the carbon balance by total organic carbon analysis at the end of the reactions, we can notice that in hydrothermal and in photocatalytic process, the carbon balance is quite high, but for the coupled process, we have a total mineralizations of all the carbon products. And in parallel, we observe high formations of CO2 in the gas phase. So the coupled process, coupling hydrothermal conversion and photocatalysis, we maximize the mineralizations of carbon substrates. So let me go a little bit further. Let me compare the three processes, pure hydrothermal, pure photocatalysis to the coupled process with two pure phase, pure annotate, the UV100, and the pure rutile. The conversions is presented on these two figures for the three process. And we can notice in anaerobic conditions, in absence of air, the pure photocatalytic process does not lead to high conversion of glucose explained by electron-hole recombinations. The hydrothermal process and the coupled process leads to quite similar conversion of glucose with time. Let us discuss about the selectivity of this transformation. So we do not observe synergy when we assisted the hydrothermal process with irradiations. And let me discuss about the selectivity. Here, this curve represents the yield of the products with the conversions of the glucose. And in the case of pure hydrothermal process, we observe as main product gluconic acid formations. When we add UV for the coupled process, we observe a disappearance of the gluconic acid formations, and the main products is, in that case, surprisingly, levulinic acids. And in the gas phase, we observe also ethylene formations. So about the formations of ethylene by photocatalysis, in the literature, these molecules was reporting as a possible products of lactic acid transformation by dehydrations into acrylic acid and under UV formations of ethylene by decarboxylations. Let me describe you what is the impact of the temperatures on this coupled process. When we perform the process at 150, we observe an increase of the rate of conversion of glucose at about 120 degrees Celsius. And in parallel, we observe also an increase of the yield of levulinic acids. In the gas phase, we observe also the increase of ethylene formations, and only at 150 we observe the formations of hydrogen. Let's go more in detail about the formations of levulinic acids by the two processes, in absence or in presence of irradiations. We can notice the formations of levulinic acids in the coupled process, but if we perform the pure hydrothermal process at higher temperatures, 150, we do not detect levulinic acid as product. And this is an advantage as regard to the formation of levulinic acid, which is the commercial products. Usually, levulinic acid is obtained from simple sugars at high temperatures or using very strong branched acids, soluble branched acids. And in that case, we can produce levulinic acids at quite low temperatures in absence of strong branched acids. So we have an evident gain of energy and safety as regard to the formation of these important platform molecules. So, but the formation of levulinic acid is, we need to understand more about its formations. And it's clear that levulinic acid is obtained only in high yield in the coupled process. And what is known is that levulinic acid is obtained following this pathway, starting from glucose or fructose in the presence of branched acid, which can promote the dehydration of the C6 sugar into HMF and its rehydration into levulinic acid and formic acid. As I told you, in the industrial process, strong branched acid as sulfuric acid is used even at high temperatures. But in the case of a pure anatase phase, we have shown that we do not have branched acid sites at the surface of this catalyst. So the question here is, what is the origin of the enhancement of production of levulinic acid in the coupled process? So to try to know a little bit more about the formations of levulinic acids, we underweight the conversion of fructose in the coupled process. First, in the pure hydrothermal process, in absence of irradiations, starting from fructose, we obtain gluconic acid, but also HMF. Almost no levulinic acid, but when we perform the conversion of fructose in the coupled process, again, we have maximized the formation of levulinic acid and formic acid. And in order to clarify even more the formations of levulinic acid, we do not start the irradiation at the beginning of a reaction when we start the conversion of glucose, but after 4 hours. And when we start irradiation, we notice the decrease of the gluconic acid formation and the increase of levulinic acid. So clearly, levulinic acid formation is due to the irradiation. But how? The question is, how could UV create branched acidity? So we do not have direct spectroscopic evidence of the formation of branched acidity upon irradiations, in addition in aqueous media. But we propose that since we are working in hydrothermal conversion, and one of the characteristics of hot water is the water self-protolysis in proton and hydroxide ion, we propose that the creation of positive holes on the surface of titanium dioxide upon irradiations may react with the anion and form the hydroxide radicals, and this is a way to shift the equilibrium of water self-protolysis, and in that way we may increase the pool of protons in the reaction media. The same mechanism might be true if we consider also the dissociation of the carboxylic acids in protons and carboxylate anion. The carboxylate anion may react with the holes and form the carboxylate radicals, and it very right shift the dissociation equilibrium of the carboxylic acid, and these two phenomena might contribute to increase the pool of photons in the water media. So that was the explanations we proposed to explain why levulinic acid is increased upon irradiations. So, and to summarize all the products we observed in the coupled products, we can say that the products is the results of both processes. First, the hydrothermal one, which is promoted as well by the bunch of the basic sites and the Lewis sites, producing all the short sugars and all the different short carboxylic acid, but also the gluconic acid, which can be formed by the oxidation promoted by the basic sites, and the features of this coupled process is the formation of levulinic acid in high yield, which can be promoted by more protons in the water phase due to the irradiations. So, assisting hydrothermal glucose transformation by photocatalysis, we can remember some important point we have evidence, to my knowledge, for the first time. In aerobic conditions, we enhance mineralizations, and in anaerobic conditions, we enhance levulinic acid formations, tentatively explained by the creations of Brunstedt acidity upon UV irradiations. And an advantage of this process is a gain in energy and safety, since we are able to produce high yield of levulinic acids at low temperatures and in absence of strong Brunstedt acids. And we have also the co-formation of hydrogen of ethylene, which are also molecules of high interest. So, I would like to thank my colleague, first Chantal Quillard, which is an expert in photocatalysis, and also the student, PhD student, Dr. Insaf Abdouli, for the huge works she did on this coupled process, and my colleague Marion Eterno and Frédéric Dapos, who are engineers in the teams. And I would like also the French agency for the financial support, and the lab and the CNRS for all the facilities. And would like to thank you also for your kind attentions. Thank you for listening.
Thank you, Nadine. Very nice presentation.
Thank you.
Very interesting results. Some questions. Now the session is open for questions. If you have a question, you can write in the chat. Pessoal, se vocês têm perguntas, vocês podem fazer aqui no chat em português que eu posso traduzir, tá bom? I have some questions, Nadine. Are the electron-hole recombination and the band gap energy important for the conversion of glucose to bioproducts like fructose? And if you did take into account or did some characterization to obtain this information?
I didn't hear the end of the sentence. Thiago, if you can repeat.
And if you did some characterization to obtain this information about the band gap energy and the electron hole recombination.
You asked me how to measure the electron-hole recombinations during the course of the reactions. I'm not able to do that. I'm not an expert in photocatalysis. Maybe my colleague can answer these questions.
Okay.
How to evidence the electron-hole recombination? This is evident when we perform, for example, the photocatalysis experiment only under neutral atmosphere by comparison to the oxygen atmosphere. In that case, the conversion of the glucose stops rapidly due to the electron-hole recombination. We do not have direct evidence of these recombinations, but we have indirect proof by the fact that the reaction is stopped directly. That was the case when we perform only photocatalysis at low temperatures under air.
Okay. This is just a curiosity. What is the composition of the reactor?
The composition of the reactant?
Yeah.
The reactant of the product?
No, of the reactor.
We started just with pure fructose, glucose. Almost no impurity in the reactant. I cannot tell you exactly what is the purity of a sugar. I can check, but I do not have the value, but more than 99.9, I think.
Okay, thanks. One more question from the audience. Joseita Costa asks you, congratulations first, great lecture. In the photocatalytic process, it's viable to use other semiconductors with smaller band gap energy in the conversion process.
Probably, the continuation of his study was to investigate different semiconductor and so on, but we wanted to make many things at the beginning, but it was so complex. We just started with glucose, commercial TiO2, but we have so many things to do. I think, of course, it is of importance to use other semiconductor with smaller band gap.
Okay, more questions? Okay, Nadine, thank you again. Very nice presentation.
Thank you. Thank you again for the invitation, this opportunity. I was very happy to present this new project. Maybe this is, how to say, it's not easy to understand everything during the first presentation because we have a mixed process. And I think it takes time to have questions and so on. So thank you for listening. Thank you for the kind invitation. Okay. Good continuation.
I hope the next time you face to face it's better.
Probably. I hope also.
Thank you.
So,
bye.
Thank you. Bye.
Olá, bom dia a todos. Brilhante palestra, né, Thiago? Parabéns também pela mediação. Nós vamos encerrar essa sessão. Obrigado pela presença de todos e vamos então lá para a sessão de apresentação dos trabalhos recentes, ok? Continue conosco.